In the previous video, we looked at the system of equations x plus y equals 3, 2x minus y equals 0. We were able to find a single solution to that particular system, namely the solution was x equals 1, y equals 2. We showed that algebraically using the elimination method. We also looked at the graph of this particular system. So we graphed both of the lines represented by each equation and showed that they intersected at the point 1 comma 2. We're going to look at other possibilities for systems of equations. So if we considered another system, x plus y equals 2, 2x plus 2y equals 4, if we went through the same elimination method with this particular example, and I'm not going to go through the work here, but I do recommend for practice, you sort of pause the video and try this out. What we'd find is that we would completely eliminate one of the equations. So we would eliminate all the terms. We'd end up with an equation that had the form 0 equals 0, and the other equation would be sort of the same as it started. And what we can see from the original setup is that the second equation is just twice the first equation. So basically, any values that satisfy the first equation for x and y are going to also satisfy that second equation. If we were to graph these two lines, we would just get, basically the same line. These both would represent a line of slope -1 going through the point 0, comma 2. And what we can kind of identify here as the solution or solutions to this are any points x, y that satisfy either of these two equations are going to satisfy both of them. So there are actually infinitely many solutions to this. You might try and come up with a few on your own by either algebraically looking at the equations or looking at the graph. We can pick out, for example, 1 comma 1 as a solution, so x equals 1, y equals 1, or 2 comma 0, x equals 2, y equals 0, so on and so forth. We could also have, sort of fractions in there. So we could have 1.5 comma zero point 0.5 as another solution, or negative numbers, right? So you could sort of go through and try and come up with all sorts of possibilities, but there are infinitely many solutions, and any solution to one of these will end up being a solution to the other. So we saw in the previous example a unique one single solution. Here we had infinitely many solutions. Here's another example, x plus y equals 1 and x plus y equals 3. And again, if we tried to go through the elimination method here, which again, I recommend you do on your own, what we'd find is that we would eliminate all of the variable terms in one of these, but the constant term on the right-hand side would not be 0. So what we'd end up with is something like, 0 equals 2, for example, for one of our equations, which last time I checked is not true. 0 does not equal 2. And what that tells us is that this particular system has no solutions. What we can see is that if we were to graph these, we would end up with two lines that have the same slope, but actually different y-intercepts. And so looking at them, we end up with these parallel lines, no points of intersection. So this is kind of the geometric situation we would end up with when we have no solutions. Remember, geometrically, we have solutions being represented by points of intersection of these lines. So kind of summarizing everything we saw in those previous examples, if we're looking for solution sets to linear equations, at least based on these three examples, given a set of linear equations, there are either infinitely many points, exactly one point, or no points that satisfy every equation in the set. That was certainly true of the examples we saw here, and one sort of a maybe surprising and very interesting fact we're going to learn in linear algebra is that these are the only three possibilities that we will end up with for any sets of linear equations. That means we can have any number of variables, any number of equations, and the only possible sets of solutions will either be infinitely many, exactly one, or no solutions. Obviously, that infinitely many sort of leads to a lot of possibilities potentially. So we're going to kind of break that one down further as the course goes along. But kind of interesting. We can't have a system that has, for example, exactly two solutions or exactly three solutions. We either have one, none, or infinitely many. And hopefully, besides these three examples, we will be able to convince you of that further as the course progresses.